gates and circuit diagrams are a way to visualize Boolean algebra. And these objects, gates and circuits, can actually be built using semiconductors. So typically the way it works is you have some Boolean algebra, you create a huge circuit diagram that you want out of it, and then a circuit diagram can just be printed onto a semiconductor, and that's how electronics are built. So what are gates? Let me first. So remember, in Boolean algebra, we had 0 or 1, were only numbers, and we had multiplication, we had addition, and we had conjugation or inversion, whatever you want to call it, which changes 0 to 1 and 1 to 0. So these are 3 operations and 3 numbers, and these are encoded using these 3 gates. The first one corresponds to AND in propositional logic, and hence to something called the AND gate. And it's written like this with a semicircle. The second one corresponds to OR in propositional logic, and hence is the OR gate, which is written like a curved semicircle. The third one corresponds to negation in propositional logic, and here it's called the NOT gate, and it is written as a triangle with a circle in front. And what these gates are doing is, if you feed in inputs, let's say x and y, where x and y can be either 0 or 1, then the AND gate will produce x times y. The OR gate will produce x plus y, and the NOT gate does not need 2 inputs. The NOT gate is just 1 input, x, and it produces the inversion of x, or the conjugation of x. And that's it. So there is no new math. It's just a visual representation. And you can use this, for example, to represent the laws that we have, the identities that we have seen so far. So let's see what De Morgan's law look like using gates. So the first De Morgan law says that if I take negation of AND, it becomes an OR, and AND for us is multiplication. So this is the first De Morgan law. And now I'll put brackets so that it's clear what we're doing. So first I need to take 2 inputs, x and y. First I need to AND it, and then I need to invert it. So this will look like, let me do this carefully. So I'll start with x and y, and then I'll AND it, and then I will flip it. So here I'm creating xy, and here I'm creating x bar, xy bar. And De Morgan's law is saying that this is always equal to x bar and y bar, and then taking their on and taking their OR. So first I need to, so let me create the right hand side. First I'll start with x and y again as usual, and then I will flip them. So this produces x bar and y bar, and then I'll take their OR. And that's it. So this is what it's saying, that these 2 diagrams produce exactly the same results. A diagram that is built using gates is called a circuit. That's it. So this, we are looking at the circuits for De Morgan's laws. Similarly, the second De Morgan law says that, I'll just quickly do it, x bar, x plus y bar is x bar times y bar. And here I'll get first an OR. I'll input x's and y's, and then I'll flip it. This circuit is giving the same output as the circuit if I were to first flip and then AND. So that's how you can convert any expression in Boolean logic, any expression in Boolean algebra into circuit diagrams. You can also reverse the process. So I've drawn something, it takes a while. So the question here would be, determine the Boolean expression. Oops, there's an extra line there. Corresponding to the following circuit diagram. Right? So if I give you a circuit diagram, we can convert that into a Boolean expression just by following all the gates carefully. So first thing, whenever you're given a Boolean circuit diagram, is to figure out what the gates are. So first I have an AND gate here, I have an OR gate here, I have another AND here, and I have a negation here, which I'll leave it as it is. And remember that AND is multiplication and OR is addition. So with that, we're ready. Now, what are the inputs for the first AND? So first AND is getting input X and Y. So this will become X times Y. That's the output here. So for each gate, you should figure out what the input is and what the output is. Now let's look at OR. For OR, the lines are coming from above, but they are just taking in X and Y. So here, if you want to clarify, it's X and Y here. And OR is addition, so this will become X plus Y. Now, the inverter, or the one that negates, changes XY to XY bar. And now AND has inputs conjugation of XY and X plus Y, and it's going to multiply these things together. So for final result I'll get is bar times X plus Y. And so the answer is that this logic gate, or this circuit diagram, corresponds to the Boolean expression XY bar times X plus Y. This is really fun. I hope you practice a lot of problems in the book. And there are many websites where you can play around with logic gates, where they're all free, and just you can play around with them and see, for example, the laws of proportional logic in action. You can also build a computer. There is a website called the NAND. There's a game called the NAND game, which lets you create a whole computer just starting from these basic gates. So you can do addition, multiplication, and create addition of multiple digit numbers, multiplication of multiple digit numbers, and so on and so forth. So you can create an entire CPU just by this basic mathematics. There is nothing more that's needed. Yeah, so that is all I want to say about gates and circuits.